I'm Anna Jane. I'm a biomedical engineer and I'm the team lead.
My name is Ruby Hackenjos. I'm the team's procurement lead and I'm a systems engineer.
I'm Thomas Ciccarelli. I'm an optical engineer and I have experience in the clean room and nanofabrication.
I'm Nestor Garcia. I'm an electrical and computer engineer and I'm the electronics lead of this project.
Hi, my name is Chris Curtis. I'm a mechanical engineer and I'm the team's CAD modeling lead.
Hi, I'm Isa Alkode. I'm a mechanical lead for this team.
Together, we are Team 24026, or the On-Instrument Slide Temperature Measurement System. We are sponsored by Roche Tissue Diagnostics and mentored by Pat Caldwell.
The Benchmark Ultra is an automated tissue staining device developed by Roche. As part of the staining procedure, glass slides are placed on individual heater pads, which are used to heat the slide to specific temperatures. Tissue staining requires precise temperature control to produce accurate and reliable staining results, which allows for diagnosis and a pathway to treatment. Currently, there are no existing devices that are suitable for accurately measuring temperature across multiple points over the surface of a glass slide placed on the heater pads, which brings us to our project, where we were tasked to create such a device.
Our design comprises a thermistor sensor assembly connected to an interface board via ribbon cabling, aimed at measuring temperature across the surface of a glass slide sitting on a resistive heating pad. The sensor board houses 6 thermistors, measuring changes in resistance across the heater. Thermistors demonstrate a nonlinear relationship between resistance and temperature, which can be described by the Steinhart-Hart equation. Through calibration data, the resistance change of the thermistor can be accurately converted into temperature readings. Utilizing an analog-to-digital converter, the voltage across the thermistor, which varies with temperature, is digitized for processing by a Teensy 4.1 microcontroller. This microcontroller facilitates communication with a host device, such as a computer, via USB. Temperature data from the thermistor is then logged and displayed on a computer. A heat transfer model of the sensor assembly was developed using ANSYS Discovery in order to simulate the temperature distribution across the glass slide and determine the delta T between the slide and various thermistor assembly configurations. The objective of the model was to optimize heat transfer within the system and provide accurate temperature readings at our desired accuracy range of 40 to 100 degrees Celsius. Several simulations were done in ANSYS experimenting with various parameters and assembly configurations, and the model that yielded the best results was a sensor board crafted from FR4 with a thickness of 0.4 millimeters. The sensor board was bonded to the glass slide itself using thermal epoxy to enhance the system's heat transfer. And here is a plot based on the results of the model showing the expected temperature transfer of the system.
We were tasked with creating a device that can read the temperature across a glass slide. This device will be used as a validation and verification tool used by Roche technicians only. It will be portable and move from heating pad to heating pad in the Benchmark Ultra device. We do not have safety requirements as this device will be utilized in a lab environment by Roche technicians and it is not going to be distributed to the public. A few requirements of note are the system shall provide accurate temperature measurement within plus or minus 1 degree Celsius. The system shall be able to measure temperature between 40 and 100 degrees Celsius, and the encasement for the system's electronic components shall be IPX4 water resistant. We have our system architecture, which shows our system split into 3 subsystems. We have the thermistor sensor assembly, which will be collecting the data, the sensor interface assembly, which will be processing the data, and the user interface, which will be displaying the data.
Our design uses the printed circuit board with 6 thermistors attached. From the ANSYS modeling, we decided to attach the glass slide to be heated up directly to the thermistor board by way of thermal epoxy. This thermistor board is attached to the sensor interface board by a ribbon cable. The interface board is protected from water damage by a 3D printed, sealed encasement. This is where the resistance measurements taken by the thermistors are interpreted into temperatures. Finally, that information is transmitted to the user interface where it is displayed on a thermal map of the glass slide. Our requirements were verified by either inspection, demonstration, analysis, or testing. Our system was designed to meet all of our functional requirements, such as employing 6 total thermistors and designing the system to be simply 2 major, durable sections that can be moved around from machine to machine. The size and shape of our device was also designed to integrate easily with the Benchmark Ultra and provide easy use for technicians. The most important requirement of our project is that our device measures the temperature of the glass slide with an accuracy of at least 1 degree Celsius over a range of 40 to 100 degrees. This will be verified with tests with precise reference sensors. Finally, the casing around the sensor interface board was created to provide water resistance to any potential splashes that could occur, and this was tested by submerging the entire encasement in water without any leaking inside.
As described by Thomas, our system is designed to accurately measure the surface of a glass slide, specifically in one of Roche's benchmark Ultra machines. In order to verify the accuracy of our system and calibrate as necessary, we put together a completely independent reference measurement system comprised of several high-accuracy surface sensors measured with a Tektronix high-precision pre-calibrated DMM. The testing consisted of setting a benchmark Ultra slide drawer heater to varying temperatures and measuring with the reference sensor first, followed by 2 thermistor sensor assemblies, thus replicating the measurement conditions for each sensor assembly. In doing so, we observed the following temperature differences between the measured temperatures and the actual temperatures for each sensor on each thermistor sensor assembly. As expected, but marginally higher, because of mechanical issues related to thermal expansion of different materials, we observed that the performance not only degraded as the applied temperature increased, but there are also significant discrepancies between sensors within the same assembly. Nevertheless, considering the consistency of behavior within and across the two assemblies, a calibration was implemented to yield the desired accuracy. This was accomplished by correlating the raw sensor readings to the reference measurements and generating calibration polynomials for each sensor. A statistical analysis performed on the calibration of each sensor assembly yielded excellent and similar results, further validating the confidence in these calibrations. Calibrating the original raw sensor data with their respective calibration polynomials yielded the results seen here on the screen, where it is evident that each reading falls well within the desired accuracy range, represented here by the yellow shaded region. Further testing, independent of the calibration dataset, has been conducted, and the results continue to support the calibration that has been applied to each assembly.
So our sponsor, on April 29th, we are going to deliver the working prototype with the data analysis in a zipped file. On April 30, we are going to submit the final report in a PDF format. And on May 2nd, we will be presenting the findings in a PowerPoint at Roche.
The process to use our device is simple and straightforward. First, the thermistor assembly is placed on the heater pad of the Benchmark Ultra. The sensor interface is then plugged into a computer and the user interface program is run. Then the heater pad is turned on, heating to and holding at temperatures of 40, 60, 80, and 100 degrees Celsius. The sensors begin collecting and displaying data in both a thermal map and a graph as the temperature increases. The data can either be calibrated automatically during the run or calibrated afterwards. This project helps us to understand the importance of modeling as early as possible to influence the design throughout the process rather than making changes to an already created design. The largest problem we had to overcome was finding an adequate method of verifying the accuracy of the system. Since the accuracy had to be within plus minus 1 degree Celsius, the verification method had to be much better than that in order to prevent the compounding of error of the verification method and the thermistors themselves.
We'd like to thank the Roche team for their support and feedback throughout this project. We'd also like to thank our mentor Pat for his advice and guidance. And finally, we'd like to thank the Pareka Lab and Kara for allowing us to use their equipment for testing and validation.